At the outset, let me thank the organizers for this wonderful meeting, and it's been a great learning experience. And I also thank all the speakers who have been part of this initiative. Uh, it's something which we should emulate going further more and more. So thanks for the initiative. So I know it's a hard task to actually fill a talk between you and your lunch. So I'm going to actually just ensure that we'll probably actually stick to the schedule. And the topic of discussion, what I've chosen to speak about is mainly related to this elastic light scattering. So one can also actually call in the modern terminology topological light scattering with an elastic variety or something like that. So the plan of the talk is to start with some very basic introduction to the light-matter interaction from the scattering viewpoint, and also look at the scattering measurements in the momentum space. A few speakers have already actually been alluding to this particular concept of K-space measurements. I'm going to just give a brief kind of overview because there are also a lot of students. And I'm going to show how we utilize this particular type of measurement to extract some meaningful information in the K-space. I've chosen two examples, but I'm going to also give a few more references as and when I come to this particular concept. One specific theme I've chosen to speak about is to correlate topological charge and kind of map it to a pattern recognition problem, which probably has implications if you want to utilize it in, let's say, machine learning and other kind of processes. Then I'm going to show you that it's important to actually incorporate absorption while looking at any kind of interactions. And it brings in a very interesting concept of the optothermal tweezer. And I'll be showing some of the experiments. One can actually now take it to slightly kind of a different limit altogether and introduce some kind of a thermoelectric effect because of an optical component, which is going to introduce some interesting effects and hopefully also help you to trap and tweeze structures down to the single molecule limit. And I'll, of course, conclude with some kind of overview of the stuff what we have been looking at. Now, let's look at the specific aspects of the basic elements. If you look at the generalized concept, this is an equation which you will find it in one of the very famous books, which actually is quite well known to this audience, I assume. In fact, also for the students, this is probably one of the best books to get introduced to learn about light scattering, especially from a classical electromagnetics viewpoint. And of course, there are many others, but this is something which you would probably enjoy reading too, because Craig's books are also worth reading for various different reasons. Now, if you look at this particular concept, the specific aspects of the interaction is to just take an incident light, you have an obstacle, and you're now looking at this scattered light. And this particular scattered light actually can be now cast into the formalism of a scattering, which is essentially an equivalent of an excitation plus a re-radiation. Okay, and this particular concept is very crucial because one can also look at this particular interaction as an interference effect between the incident beam and also the scattered beam, and therefore the collective effects what you're going to see has some very interesting structure to it. Now, going further, the geometry of the problem, what we are interested in, it can be understood from the specific formalism. You have an incident beam, you have a scattered structure. Now, you're looking at this particular interaction in the context of the angles, which various authors, the speakers have already mentioned in some particular part of their talk. But what we are interested in is to look at these azimuthal angles phi and also the polar angles theta. And I'll show you how we actually go about measuring these kind of angles in a systematic way, specifically in the context of a tight focusing condition. In fact, that is something which is of relevance if you want to also characterize these optical beams which carry some specific structure. How do you really go about looking at the momentum space signature is a topic of discussion. Now, going further, we'll now look at the specific aspects in terms of the measurement what we are now interested in. Okay, there is a phase delay here. One of the things which is very fundamental to understanding the momentum space imaging is this concept of Fourier transform picture of a lens. This is something you would probably come across in various different textbooks, including probably one of the best, in my opinion, which is the Goodman's book, where you will actually look at this particular plane, which is the object plane, and you ask for a particular angle of the emission from that particular object plane, what is the signature you get in the K plane. So for every particular angle you define in this object plane, there is a specific point in the momentum plane. And this particular point is now characterized by angles, and those angles are what we are interested in. And we'll look into this in slightly greater detail. Now, you can also look at this, as I mentioned, from a slightly specific application viewpoint. Whenever you perform an experiment and you're looking at objects in an optical microscope, you would be looking at the sample plane. You will have a high numerical aperture objective lens, and you will now ask for this particular light which is emanating from the sample, how do I map it? One of the elegant ways to do this is actually to capture the so-called backfocal plane image, which essentially is a Fourier transform of this particular light which is emanated and projected onto this K plane. But if you take a very high numerical aperture objective lenses, the backfocal plane generally is inside the lens. In fact, that is actually something probably people who do high resolution microscopy would be aware of. Therefore, what one can do is actually to take this particular principle and introduce cascades of lenses. How do you do that? One of the ways to do it is actually take this particular lens, you take the light into the backfocal plane and introduce something called as a tube lens. And there is also a field lens which is also called as a Bertrand lens. This is something you will actually hear people doing Fourier microscopy use it extensively, because what you are essentially doing is taking this backfocal plane image and relaying it to a different point which can be placed outside a particular point of your optical setup. And I'll show you how this particular setup will be very useful if you are now trying to do something called as pupil function engineering and other kind of things. The meaningful information what you're going to get in such kind of experiments are now characterized by two angles. One is the so-called polar angles, which essentially is the numerical aperture of the lens. This can also be projected as the ratio of the wave vectors, and that's the reason why it's also called as a momentum space imaging. The other angle, of course, is the azimuthal angle, which is now the angle within that particular plane, what we are now looking at. We also have detailed this particular viewpoint in a specific context. For example, if you look at, let's say, light scattering from a single object, for example, a kind of a meso wire made of silver metal, you would end up actually getting this scattered light, and you project it, and this is a measured Fourier plane image. I'm going to show you extensively. So what I would guide you towards is to just look at the kind of image you can capture. Do not worry about the words which are written in this particular image, because they are related to some specific kind of a measurement. What is important is to now know that you can now plot this intensity as a function of the two specific angles. One is this azimuthal angle, and other is the polar angle. If you also look at this particular angle, you can readily see that these are the angles which you subtend when you have numerical aperture of the lens which are defined. Yes? This is actually a nanowire. It's a silver nanowire. I'm going to show you. In fact, I'm going to go to the specific case. I'm just laying out the foundation for the measurement. I'm going to further go ahead. Now, you can also now look at such kind of scattering processes from a viewpoint of energy momentum spectroscopy. In fact, what does that mean? Instead of just now only looking at the light which is emanating from the Fourier plane, you can now put a slit onto that particular Fourier plane and extract the energy dependence of the light distribution. So what you will end up getting is the distribution of the energy. In this particular case, it's a Raman shift, what we are looking at, as a function of, where the momentum space distribution of the light is plotted on the x-axis, on the y-axis, and the x-axis actually gives you the energy distribution. So all you are now doing is essentially getting a k versus omega kind of a viewpoint, and hence a dispersion kind of a relation can be set up in this particular framework. Now, there's a lot of details here for students and other people who would want to really kind of get an overview of this. I would urge you to just have a look at this particular review article. This is also available on the archive, and you will be able to get all the information. I would also suggest you to have a look at a lot of work which has been done and developed over the years by groups of Novotny, Van Hast, Kernrink, Peter Banzer, who has been using this technique very effectively in the context of structured light. Maybe some of you would be recognizing that. And Zia and Cozier have used it in a specific and different context. For example, Zia has used it in the context of 2D materials to measure the dipole orientation, etc. So this is actually a very well established technique, but it dates back to some of the old experiments, what was done in the context of single molecule dipole orientation. For example, people who do liquid crystals are aware of the technique called as conoscopic imaging, and that is essentially the same principle. It has been done for over 100 years or so, but in the context of tight focusing and in context of microscopy, this has been rejuvenated, and there is a lot of interest in looking at this particular interaction. In principle, you can, but there is some constraints there, because then you have to orient your molecule accordingly. And then you can extract the information in an orthogonal axis, which is a challenging experiment. Yeah, but in principle, one can actually look at that. Now, this is actually the design which we have implemented in my lab. It actually is kind of a, jokingly I tell, it is some kind of a Gaudi's building. It is always under construction. So there is always something which you can add to whatever we have been doing. So it can perform K-space imaging, dual channel holographic optical tweezers, which I'm going to talk a little bit in the second part. Particle tracking, we can go and push the limits to fast imaging too. And dark field imaging, both in coherent and white light kind of a configuration. And the scattering processes and also the nonlinear excitation. So it's kind of a combination of various different techniques. It's a home-built setup, and it is quite useful to look at this interaction in a significant detail. Now let's go ahead and see in what way one can utilize this. I'm going to briefly touch upon the two concepts which we have been working on. The first is the topological charge and the pattern recognition of the charge, these specific elements, and how do you really go about performing such measurements. So one of the questions we were interested in is to look at a method to read out the orbital angular momentum through a scattering pattern. Okay, so the question you ask is, can you utilize a scattering the signal what you emanate from this kind of a process, and ask how can you read that particular topological charge. The central idea is the following. You essentially have a structured beam. In this particular case, it's a Laguerre-Gaussian beam. You are now scattering that light through a reasonably high numerical aperture objective, but collecting it with even higher numerical aperture. Okay, this is actually quite in contrast to some other techniques. For example, in optical trapping, you generally do the other way around, or even dark field imaging. So what one does is now look at the scattering pattern. So for example, if there is no nanowire, you can see that there is now an optical vortex with a 0 at the center. But upon
what's the basic idea about using this higher numerical aperture collection system?
Larger angle, exactly. That's one of the reasons, because your collection efficiency is much larger. See, your illumination is only this much, whereas your collection actually is a very large angle. Second point is that you also can collect something called as forbidden light, which is essentially the wave vectors which are very large, and therefore you get more information in the scattering pattern. So the idea is now to look at the scattering patterns, and the systems what generally we use is it's all far field. Everything is far field. Everything what I'm talking about is far field. No. I'll show you that you actually can convert the so-called evanescent waves into propagating component by using a scatterer. That's the crux of the idea. Now you can use this particular technique, and this is actually the most important part. In fact, something which we were talking, Nirmal, this is something very specific I was mentioning. The issue why we can actually do this kind of measurement is that we perform the so-called dark field scattering in the collection mode. So the idea is to actually have a laser beam, kind of projecting it to the SLM. You create the beam of your choice of any specific kind of structure. Therefore, you do not want this dark field approach to be inculcated in the illumination path. All you need to do is then you actually have to collect this large, with a high numerical aperture lens, use the specific pinhole, and using this Fourier plane imaging technique, you block using a stop. And this stop essentially ensures that the vectors which are directly coming from the incident light is completely blocked, and only the scattered light actually reaches the detector. And this is a very powerful technique, you will see, because you are no more constrained by the numerical aperture of the excitation lens. This is a major constraint if you do white light dark field scattering, which I will also show you how we do it. The reason why this is also important is that you do not want to play around with the structure of the beam. That is the whole point why you are actually doing this experiment, right? Because you want your structure to be preserved. You want to look at the scattered light from that particular structured beam and then collect the signal thereafter. Now, what do you learn from such kind of interaction? You will actually see that you essentially have a Gaussian beam. You will now have a projection of this Gaussian beam in the momentum space. And this is actually the simulated result. You'll see parallelly most of the stuff what we show is generally the experimental data and the numerically simulated data. If you now introduce, let's say, a Laguerre Gaussian beam which is carrying a topological charge -1, it would actually have specific kind of a lobe structure. And you can now take, let's say, a Hermite Gaussian beam with a specific index, and you'll also simultaneously get this particular kind of lobe structure. So what this is actually showing you is that you can first of all discriminate between different kinds of beams to begin with from the pattern, and now actually you can build a story from there. Now, one of the main issues is actually to look at this particular topological charge. Yes. Yeah.
So the LG, so what you're basically looking at is you're just comparing the simulation to the experimental, right?
Yes, yes.
Simulation with the LG one, I see some kind of a tilt in that those two lobes, right?
Yes, you're right.
Is that there in the experiment?
Yeah, we actually are blocking the incident vectors.
No, that is the second one, right? Which is the one? So it is the top two, I mean the upper and the lower one you're comparing? Or how are
We are comparing upper and the lower.
so the second one, for example,
Yes.
LG0 -1.
This one.
That lower one has a distinct tilt, right? So maybe the picture is not clear.
Yeah, there is actually a tilt. If you come closer, you will actually. Yeah. I'm sorry. Maybe that's probably not relayed properly.
Pixel to pixel cross correlation?
Yeah, no, we don't do pixel. We see the pattern kind of distribution of intensities. I'll show you how we quantify it. This is an important question because otherwise you will not be able to justify the pattern recognition.
There are like two things which are slightly similar. Then how do you
Absolutely. In fact, I'll show you that that's one of the key points. There is actually a number counting which you can associate with this. For that tilt actually is essentially coming because of the orientation of the wire. There is a small kind of angle because you cannot precisely place it with the Fourier plane. Yeah, no. This is in this particular case, it's carrying only the structure in terms of the LG beam.
But it's literally polarized input?
This is actually linearly polarized. Yeah. Now,
Circular polarized, we have actually seen after focusing, it actually tilts.
yeah. You are absolutely. In fact, I'll show you some of the stuff exactly coming to that point. Yes.
But this tilt that he is talking about can also because of the angular momentum charge. That is what the essential TIFR single slit.
I'll come to that. If you can wait for a few minutes, I'm going to actually come to that particular point. So now you would actually be able to discriminate the topological charge such that you can map for every L what you will have L plus 1 number of lobes in the Fourier plane. This is actually the mapping which is very consistent. If you would be able to verify this even using rigorous diffraction theory, including corrections related to the Kirchhoff's law and other things. Now, this is something which can be utilized. Okay. And for example, you can now take the higher order beams. So you can clearly see that as you go higher and higher in the topological charge, the number of the patterns what you get actually perfectly increases. So there is a one-to-one correspondence, and you can do the mapping very efficiently. Now, going further, you can actually also discriminate between the sign of the topological charge. That's obvious because now you have a very clear scattering pattern. So I'm not going to spend time on this. Instead, what I'm going to do is actually now we calculate it. We actually use specific theory related to the Debye-Wolf's theory. No. First, what we do is we also use something called PyFocus. I assume you would have heard about PyFocus. It's actually a Python-based suite, which is very powerful. You can also cross-verify using COMSOL if you want. That can be done in principle, but we generally use the other open source sources we have been using. No. There is no. I at least I don't use it. Yeah. You can actually use MATLAB codes also to do it. Of course, it depends on how much kind of capability you have in computation. That's all. Now I'll quickly go to the simultaneous detection. There is actually a delay between here and there, which is not ideal because when I play movies, I am a bit worried now. Okay, the idea is that you have a structured beam which can carry both spin and orbital angular momentum. And this is something which we have been discussing for the last few days. What is interesting is to ask, can you simultaneously detect these particular angular momenta in the context of the experiments what we are now looking at? So the question is, for example, if you come with sigma plus and sigma minus, which essentially is a circular polarized version of what we are now talking about, and then it also carries a topological charge. Now you will look at the scattering pattern. So before that, to ensure everything is okay and this particular principle works fine, we kind of try to verify this with the stuff what, for example, we have been discussing in terms of the spin densities, and we look at the optical flow of this is essentially orbital flow density and the spin flow density. You essentially combine them to see the total spin density, and you see that there is, for a specific kind of polarization signature, what you have, you would actually be able to have some specific kind of distribution of the fields in terms of the spin densities. And this gives us a bit more confidence to go ahead and perform this experiment. So I'm going to just give only one of this, but I would be happy to discuss more offline. So the issue is here that you would be now able to see specifically a very particular signature both within the so-called the allowed region of this far-field scattering and the forbidden region of this far-field scattering. And in that particular region of scattering, you would be able to now look at the intensity distributions, and you would now be able to discriminate not only the orbital angular momentum, which is now given by L+1 counting numbers, but you will also be able to now look at the density kind of distribution in terms of the intensities and map that into the to the plus sigma or minus sigma. So that is the whole principle behind this. There's a lot to this, but due to the limitation of time, I'm just giving you a gist. I'd be very happy to actually discuss this going further. Now, we have been actually looking at this. There's also a lot of background work and also follow-up work. Yes. Yes. Yeah. See, thanks for asking. The ones which are marked in orange are actually in the forbidden region. Okay, and the ones which are marked in the green are within that particular region where you. When you say forbidden, just high K vectors, but that is beyond the 0.5. Exactly. Yeah. Precisely. See, if you look at this very carefully, this is actually given. Yeah, it's 1.49. We are just plotting it 1 point. That's. Yes, precisely right. Thanks for mentioning that. That's an important point. Okay, now we have been actually doing quite a bit of stuff. Maybe because of the fact that Professor Gupta mentioned about the very interesting prospects of transverse spin. I assume he was also in the audience in one of the previous talks when we were discussing about this experimental observation of the transverse spin. In the context of plasma on polaritons, we have also been looking at this. And there are quite a lot of activities. Nirmalya and Ayan also have very interesting stuff which is going on. And of course, this whole audience actually has been looking at these concepts in a various different way. Now I'm going to switch. All of this are the same type. It's this exactly the same methodology what we want to use because we know it works and we know the theoretical kind of underpinning behind it. So we want to push the limit to see to what extent we can do. So how much time I have? 20, perfect. So I'm going to now just go to the second part of the talk, where I'm going to incorporate absorption into the discussion what we are now looking into. Most of the time it is the scattering which dominates, but you actually can now look at some effects because of the structuring of the field, where you can also incorporate the absorption effects. And one way of looking at this particular concept is in the following way. So you can now look at both the cross sections in terms of scattering cross section and the absorption cross section. Specifically, if you look at the absorption cross section, you can now compute something called as heat power density. This is essentially related to the intensity and also the imaginary part of the dielectric constant of the matter what you are now interacting with. Therefore, if you now have a specific kind of a material which has reasonably large imaginary component of the dielectric constant, you would end up actually heating an object. And this is very crucial when you take, for example, plasmonic metals, like what Zubin was also mentioning in the last part of his talk, where you can utilize some specific kind of thermal kind of radiation too in such kind of elements. So now, if you look at this, this heat power density, all you need to do is just take volume integral of that, and you'll be able to compute the total power absorbed. Now, the question is that this can this be used, of course, as a heat source? Yes, that is something which people have been working. But there's also an interesting concept and prospect of utilizing forces and torques because of these kind of absorptive effects, and that can be carefully tuned in certain experiments. So one of the ways actually to do this is the following. You take, let's say, a normal dielectric material and infuse that with light absorbing particles. In this particular case, you can take, let's say, a polystyrene sphere and then infuse it with some kind of iron oxide material. And this iron oxide material actually is now kind of subjected to some kind of an optical trapping forces. And you will see that in this particular configuration, again, we utilize a specific kind of orientation of this particular structure so that you study the evolution of this assembly, where you now have radiation forces. In addition to those radiation forces, you also incorporate an absorption effect. And I'll also show you what happens if you don't have absorption effects and what will happen if you have absorption effects. Okay. Now, just a couple of seconds on this particular system. This is again a high numerical aperture kind of configuration. Here it's a bright field configuration, and we use a fast camera. It can actually go up to 1,000 frames per second because we want to study the dynamics, and you can also further push it. Yes, yes.
It's not Aharonov-Bohm kind of.
No. This is just purely just.
It's just a pure absorption related.
Absorption related.
Ohmic process.
Ohmic process. Yeah, most of the stuff. Water. This is all in water. So now, hopefully, this is going to work. To the left, what I am showing you is the effect where you generally have conventional polystyrene beads. So these polystyrene beads are now trapped in a defocused laser beam. They are not perfectly focused, they are defocused. So what you will see is formation of this ring, very similar to what Pavan actually was talking, beautiful rings, there's a symmetry in this, hexagonal packing, etc. Now let's look at what happens if you incorporate absorption. What you will observe is that they do get kind of confined, but there is now a repulsion. So you will see that different particles evolve, or rather the assembly evolves, where another particle comes and gets kind of trapped in this kind of confinement. The crucial factor between these two pictures is that in this particular case, it's a pure polystyrene colloid. And here we actually have infused iron oxide material in this colloid. Sizes are more or less the same. It's very difficult to experimentally get the exact sizes. So we have tried to match it as close as possible. But this effect is consistent. Now the question is, why does that happen? First and the foremost is that in this particular situation, there is not only the optical force, which is essentially kind of a long-range attraction, but there is also now a thermal component which gives you the short-range repulsion. This short range repulsion also comes from a thermophoretic interaction because this is associated with the Sorey coefficient of the particle which is now getting absorbed. Interestingly, the sign of the Sorey coefficient also plays a very critical role. You can design the material so that you can now propel the particle such that this doesn't get attracted but gets actually repelled from the trap. So you can now really create large accelerations on the particle and move them around and do quite a lot of interesting stuff. Now, going further, we wanted to understand whether you would be able to now look at the effect of this short range repulsion. You can see as you increase the power, the particle actually goes off center from the illuminating beam. Mind you, this particle is still kind of trapped. Okay, just that as you decrease the power, it comes closer to the beam, and as you actually increase the power, it actually gets repelled. So there is an absorptive effect and a radiative component acting together. Now interestingly, you can switch the polarization of the trap, and you can now start looking at a momentary kind of a transient rotation. Okay, you will have to kind of observe it a little closely. If you look at it, we're going to switch the polarization y to x, you'll see a rotation now. There you go. This flipping essentially is not only because of the fact that you are now heating the particle at a different location, but the trap is also orienting. And there is a collective effect because of these both radiative and non-radiative components which are playing critical role. Of course, you can use this principle, do further analysis. We can use liquid crystals, and this is one of my favorite experiments because you take this particular colloid which is thermally active, and you dip it in 5Cb, which is a pneumatic liquid crystal, and you eliminate this particle. It very nicely undergoes a phase transition. The radius of this ring, which is symmetric because of the spherical symmetry of the particle, is proportional to the temperature. So longer the radius is, farther apart is the thermal field which is propagating. And one can actually utilize this as a calibrator. This is well known. This is not our technique. Frank Chicos, for example, in Leipzig actually has been using this method very effectively down to single quantum dots, etc. But the crucial aspect is that one can utilize this method of looking at the Brownian dynamics of the particle and then extract the mean square displacement. And from there, you would be able to now extract the trap stiffness along the x and the y direction, and hence the force acting on that particular particle. Yes? Yes?
This is now a non-equilibrium system.
Absolutely.
But then what you are using
is it? Absolutely, absolutely. You're absolutely right. In fact, if you look at this equation, we also actually use it with a lot of caveats. Okay, this is not going back. Okay. In this particular case, to me, yeah. In fact, this is specifically the lag time and the trap characteristics actually have a correction to this. That's precisely the point we do mention in the paper, because we are clearly aware of the fact that this is a system out of equilibrium. Yeah.
So you have the fluctuation theorem?
Yes. Now, in fact, if you look at my abstract, which I have given, I have also mentioned that there is actually a room for improvement for this force measurement. And the way out is a k-space measurement. Because you would essentially have a momentum vector, which is actually defined as k in. You have a scattering particle. And if you now look at the interaction between the incoming structured beam and the scattered particle, you can also now look at the scattering, this k-scat. So the idea is that if you can now effectively measure this k-scat with respect to the k in, you would actually be able to recover the forces. And the important aspect is this is independent of the equilibrium or non-equilibrium situation in which you are in.
Right, because here what you're doing is you're sort of undermining, there's an effective potential now, right?
Yes.
There's a thermophoretic effect because of hot and cold.
Yes.
Pushing it out of the trap.
Yes.
And you have, but you're using the thing where that term is not there.
Not there at all. Precisely right.
That term is not there.
Yeah.
You're still sort of finding it.
Exactly. In fact, what people have done is there is a recent PRL paper where they have used it not only on one particle. There is now an ensemble. You now actually have a machine which actually learn this, and you can compute the optical force. So you don't have to really do that.
Oh, they're using this one.
Yeah, they use, this is actually called, by the way, direct force measurement. I assume people who do optical trapping would be aware of this, because this is equipartition, mean square displacement, drag force measurement, and the fourth one is actually the direct force measurement. Yeah, this is essentially the direct force measurement. The K-space, what I was talking about, is essentially the same. Okay, now to quickly wind up, you can now also do some very interesting thing. You can make a particle hover by trapping one particle and actually having this short range repulsion, long range attraction. You can increase the power, you can make the other particle dance elsewhere. Okay, this is probably of interest to a lot of people who do various different things related to non-equilibrium, stat mech, etc., etc. So there are plenty of things one can study, and you can also look at the polarization effect. For example, then you can flip over from one direction to another direction, where you can see from Y to X, it will flip. There you go. And this is all non-contact, meaning the beam actually is at the center, and you would have spread it through a structure, and therefore you would be able to get something out. We also do Maxwell stress tensor calculations to also look at possible optical binding effects. That is something I'm going to skip, but if somebody is interested, I'd be very happy to talk. This is one of my favorite things to do in my lab, because you can really control things better in a numerical simulation compared to experiments. So that is something which is also quite interesting. Now the question is, can we push the limit towards a single resonant nanoparticle? And the answer looks kind of encouraging. If you now look at, let's say, kind of nanoparticles of, let's say, silver, gold, or any kind of semiconductors, if you take specific kind of size and under certain conditions, you will see the total absorption rate, or the heat generation, which I was talking about, the Q, can now be tuned as a function of wavelength, purely because of the imaginary part, which is actually playing a critical role. Now, the mechanism is essentially the Joule heating. It is actually also related to probably plasmon resonance, if I'm correct. If I'm specifically looking at this particular principle, there is also an absorption efficiency which goes up. Yeah. Yeah, it's essentially the extinction, but most of the time it's a scattering which contributes. Yeah, this is actually nanoparticle, 30 nanometers.
So you are referring to bulk plasma?
I don't know in what context you are talking bulk, because they essentially are probably localized plasmons, so to speak. Yeah. Now you can tune them around, so which means that the following. What we can do is actually we have come up with something called a thermophoretic tweezer. Don't worry about the Raman part, because that is actually used for single molecule detection, etc. The idea is the following. You can now structure the optothermal field by placing it on a glass substrate, a nanoparticle, and then what happens is you now incorporate some kind of ions in this fluid. And once you have ions in this fluid, there is now a very specific kind of ions. We essentially use micellar structures, which actually form beautiful kind of globules for a particular concentration, and they assemble in a different way for other specific concentration. Once you eliminate these kind of particles, now there is the gradient of temperature because of the vicinity, in the vicinity of the particle, creates a very interesting field. And that electric field gives rise to some kind of force. And this is very well known in the context of thermophoretic force. Now what we do is, we can now utilize this particular principle, and you can trap single nanoparticle. What you are now seeing is a incoherent dark field with an optical trap. What you are now seeing is a single 250 nanometer gold particle trapped on another gold particle. So you can switch on and off, the laser is on, you trap the single gold particle, and you switch that off, and it goes away. You may ask, how is the size so big? Mind you, this is actually an image. So this is actually not the actual size of the particle. What you're now looking is a scattered image of the single particle. So the advantage of this imaging method is the contrast.
How big are the particles?
This is 250 nanometer particle. You can also observe the Brownian motion of the particle going around. You can now push this further and also create a small assembly and move them around. And before that, the forces, for example, if you look at the optical force which you compute from Maxwell stress tensor, it would actually be something of a fraction of a picosecond, piconewton. Whereas now you incorporate this particular optothermoelectric effect, you essentially are creating a gradient of temperature in the local temperature in the vicinity. And there's also some bit of interesting stuff which goes on here in terms of the Sore coefficient, etc. But what you end up is essentially a force term, which is now dependent on this particular electric field and the effective surface charge density of the particle. So that surface charge density is what we are playing around in the structured field. So now you would be able to now enhance the trapping potential, so to speak, and you're able to now create a very tightly trapped potential at extremely nominal powers. And this is very important for biology and other kind of applications, because you do not want to actually use very large powers to really illuminate your biological structures. So in last 2 minutes, that's all, right? I'm almost done. 5 minutes? Great, thank you. So in last 5 minutes, I'm going to just tell you that we can also do the cargo transport, so to speak. Now what you are doing is now creating a small aggregate of the nanoparticles, again 250 nanometer particles. What you'll see, this acts like a kind of a nucleation center. This is all undergoing Brownian motion, the nanoparticles. We have been able to trap this and create a small aggregate. Now we move it. This small assembly is moving with the laser beam. Mind you, this anchor particle is still static at this location. You can move it up, left, and move it down so that you would be able to place the aggregate at location of your interest and switch off the light. It goes back to the fluid. And this is very crucial where you have to avoid clogging in microfluidic channels, etc., etc. There's a lot of implication, but really optics is the main reason why all this is happening. That is the reason why I'm actually also trying to put a word across, telling that there is actually a lot of effect which can be controlled by structuring the beam, but slightly in a different context from the first part what I spoke about. Yeah, exactly. Precisely. In fact, that's the where this is probably useful and probably looked into. We actually look at the inelastic light scattering also from this. I have not spoken anything about the inelastic light scattering here. Everything what I've been talking is only in the context of elastic scattering. This is only one slide where I'm showing the inelastic light scattered from specific kind of molecules which are there in that aggregate. What do you learn? Not anything about the spectra itself. You can learn about the electric fields. If you want to now look at the fluctuation in the electric fields, how do you really go into that particular region where there's a lot of fluctuation? You would have to introduce an element which would go there. Molecules do the job. And therefore, using surface enhanced Raman scattering, you actually can study the fluctuation. And this fluctuation, interestingly, is precisely the truncated Pareto distribution. It's an extreme statistical event where you would actually see bursts of photons coming from one particular molecule or the other molecule. In this case, we have two different molecules competing for a same hotspot, so to speak. And then you will be able to look at the spectral kind of evolution and extract the statistics and look at these fluctuations and get an information on how fields are fluctuating in that region. We can also play around with the propagating plasmons. Optical pulling is something a lot of them actually are interested in. What we can do is utilize the plasmon polaritons to now pull objects. You can now look at objects, keep it somewhere else, you pull it along the length, and you would be able to now trap them. Interestingly, you can study nucleation, aggregation, and growth. For example, if you now have a wire, a plasmonic wire, this plasmonic wire has a very strong polarization dependence in terms of propagation, because the propagating mode is excited only along the length of the wire, and therefore the heating also happens only along the length of the wire if the polarization axis is along the length. If you make it perpendicular, it will not do so. I'll show you what happens. You'll start observing crystals. When you have polarization along the length, you'll form two-dimensional crystals of colloids. And this is actually, colloids actually are called big atoms in a particular limit. And you would be able to now study a lot of interesting questions related to, let's say, aggregation and self-assembly, etc., triggered by the plasmon. we all, oh, okay, you want to see that? It doesn't, it just actually gets trapped at the location of excitation. That's all. There is no component which is propagating here. And you can do this at a slightly larger scale. This is something which we started off, and one can do some very interesting thing. We can create a large aggregate of assemblies. You can create swarms and various different things. This is actually something which we did quite some time ago. And the single nanoparticle work is essentially the kind of extrapolation of that particular concept. Okay, now for students especially, if you're interested, I've actually kind of given an elaborate discussion on how scattering and optical tweezing, especially in the context of inelastic scattering, but also in elastic scattering in this particular roadmap. This is also available. This should be out also soon in Journal of Physics Photonics. But a lot of basic concepts and references are there, and please do have a look at it. And there are also very interesting kind of concepts discussed in that roadmap. There's also one small review I've just recently written. If you are interested, please have a look at this, especially in the context of the colloids interacting with optical vortices. Because plasmon brings its resonance effects, that creates some very interesting dynamics. We have not discussed anything about the lattices of vortices. That is another very fascinating concept. I would urge you to have a look. There is some bit of orientation in that particular review. I've also kind of touched upon the so-called negative talks, which we were discussing, and where you will actually have a concept where you can have a spin angular momentum. So where the SM creates a trap of resonant nanoparticles. It creates, let's say, a hexagonal structure. So you essentially actually are coming with some kind of polarization, right? What you do is you create a trap and you trap metal nanoparticles like gold particles. This whole spin angular momentum will be now rotating this whole assembly. Now you bring a test particle like a dielectric colloid. Now the rotation direction to begin with of the SAM is in this direction. The test colloid comes in. This particular rotating structure starts acting like a gear, and the particle actually goes in the ulta direction. And this is actually called as the negative torque. And this is not my work. This is Norbert Scherer's work from University of Chicago. Very fascinating work. This is a paper in Optica. I don't know the year, but I would be able to give you the reference. The effect, why is this happening? It is happening because if you just take dielectric colloids, these effects do not come into picture. The effect comes purely because of the fact there is a multiple scattering which is happening between the resonant colloids. This actually creates a very interesting hydrodynamic field around it. So what they call is, it is actually a gear which converts a SAM into an orbital motion. And obviously there is a lot of application and interest. How the mechanism itself drives this principle is still a question. And there are a lot of interesting process. There are a lot of things discussed in here. Of course, it's a brief review, so I've just given you some overview of the topics. So to conclude, what I started was this. I told that the extinction and absorption plus scattering is important. And it is deeply connected to the topological optical momentum. And this is something I hope you would have already got it from the scattering, but the absorption also plays an interesting role. And the reason why it has been studied extensively is that it has implications in forces and torques. For example, high resolution imaging. Professor Nicholas Zerdev spoke about very interesting prospects, essentially noting the same k-space dependence. But also there is a prospect of information transfer. Need not be always quantum. It can be even classical in nature. But there is something which is there still to be explored, as Professor Senthil was also mentioning in terms of the classical picture. And the pattern recognition and other things can be used as a feedback for machine learning, etc. So the most important slide from my context is the next one, the acknowledgement. I could have not been able to actually do all these things without the group members. I generally show all the group members because if you're working in a laboratory, everybody actually has a role to play. In red, what I've highlighted is the people who took the initiative. Arindam was the first student, and now he's in Creole. He's now working on nonlinear aspects of the K-space imaging. Partha started the trapping work. Adarsh also took the K-space imaging further. Deepak was the first to also get started with the angular momentum work. Sunny and Deepta were the ones who did the trapping work. Rohit, who was an undergrad student, and interestingly, he's now become a faculty, also played a very critical role. Utkarsh, who is now in UPenn, also has contributed a lot. Current students, of course, they're all, many of them are all almost finishing, and 4 of them actually are in the heart of the experiments as I speak probably. And I should also thank all the discussion I've had over the years. Probably 16 to 17 years ago, it was Lucas from whom I actually started learning a little bit of the K-space imaging. And Craig Boren of the famed Boren and Hoffman, I really have to thank because some of his textbooks and also his writing has influenced my research. Alex, with whom I also have a grant, also has been fundamental in me kind of learning K-space imaging and other things over the years. Funding comes from Indian resource and also some from US. I am also thankful to the past funding from various international agencies for network grants, etc. And the most important thing before the lunch, thank you very much.